So today's lecture is about problems for parameter estimation, maximum likelihood estimator, maximum a posteriori estimator, least square estimator, minimum square error estimator, and then these are the measuring quality of estimator like unbiasedness, variance, consistency, the camera raw lower bound, feature information, and some efficiency and application. Okay, so today we cover only these. We focus on these first three topics. Okay, this is a content of whole chapter. Okay, today we cover this, and later and on Thursday we cover this one. Okay, so this is all about the basic estimation theory. So in the problem of estimation parameter, we will study introduction and models for estimation of a parameter. So the problem of estimating a time in varying parameter x is the following. Okay, suppose we have given the measurement set. This is any function h. Okay, you can replace by any variable. This doesn't matter. So z is our measurement. This z measurement is given by sensor. Okay, this is sensor output. So sensor output, and x is our random parameter. Okay, we are estimating this random parameter x given the measurement z, and j is the number of measurement. Okay, and w is the denotes the noises, and here j is number of scans. 1 2 3 4 5 k is not number of measurements, it's number of scans. Okay, so z of 1 scan or z of 2 scan. So suppose this is a function. So what are the measurements at j scan at for the of a random parameter we are having disturbance or noises. Okay, then find the function of the k observation. So what x of k is our estimator equals to x of k zk. So the estimate of x is obtained based on zk. Capital Z is include the measurement set, and small z is a part of the set. Okay, z is complete set, capital Z, and small z is a small part of this z. Okay, so this estimator where these observations are denoted by this one. So zk is denoted by this one, where zij is j equals to 1 to k. So that estimate the value of x in some cases. So equation 2 is our estimator, which calculates the estimate x dash. Okay, if we simply write x, this is the given parameter. We are about to estimate this thing. So if we put a cap over x, it means it is estimated value. This is simple random value, and this is the estimated value. So equation 2 is called estimator, and which calculates the estimate x of x cap of the parameter x based on the k observation. And here your x is mixed with some noise omega j. So that noise is white Gaussian noise. Now Similarly, the estimation error corresponding to the estimate is on this one. Then we calculate the estimation error like this one. X, this ascent bar equals to x minus x cap. So equation 2 can be any estimator like common filter or external common filter or some another algorithm which estimate the value of x using the observation. Observation means the sensor output. So the parameter estimation can be viewed as a static estimation parameter. If we are finding some parameter means some quantity or a feature of some object, then it is a problem for a static estimation problem. But the state estimation can be viewed as a dynamic estimation problem because the object state is dynamic. It's not static. It's dynamic. It can be can have a dynamic properties, dynamic models that can maneuver at any random instances. So state estimation is a dynamic estimation problem and parameter estimation is a static estimation problem. So we will cover these two things, okay, in later chapter when we about linear, static and dynamic estimation problem chapter. We will study these things. Now there are two models for estimation of parameter. One is non-random and other is random. So non-random is a problem for non-Bayesian problem or Fisher approach, and random problem is called the Bayesian approach. Okay, non-random means there is unknown true value x naught. So there is unknown and constant value. So we apply here non-Bayesian approach, and random parameter is any random variable having a periodic PDF p of x and a realization of x according to p of x. Okay, and is assumed to have occurred, means it have occurred. We know the periodic information of x. We already know the random variable x, and this value then stays constant during the measurement process. This is called the Bayesian approach. Like in the Bayesian approach, we find the condition probability p of x given y. Okay. So for random problem we use Bayesian approach. Normally our tracking system is a random variable. Okay, so we apply the Bayesian approach in our tracking system because we are tracking the random variable. So we have two approaches, Bayesian approach and non-Bayesian approach. Bayesian approach is for random variable. This is for the random variable, and this is for the non-random variable. Okay, so Bayesian approach starts with a periodic PDF of the parameter, which obtains its a posteriori PDF using Bayes formula. Okay, so which one is periodic and which one is a posteriori PDF? You already know this formula. So who can tell me which one is a periodic PDF and which one is a posteriori PDF in this formula? Can you tell me please? Which one variable is a periodic PDF and which one is a posteriori PDF in this formula?
Oh, px is
Periodic.
periodic and px bar z.
Okay. Yes. So this one is periodic PDF, and this is a posteriori PDF. Yeah, means we are updating this known PDF, it means we already known this value. This value is already given. So we are updating this thing with the help of this conditional probability to find a posteriori PDF. So this is same thing. 1 upon c is some constant and equals to conditional probability and p of s. So what 1 upon c is something like that. We add up, sum up all a posteriori PDF, and that must be equals to 1. We have already studied this thing. So normally p of z must be equals to 1. So we put here 1, and this is constant, normalization constant. Normalization constant. So p of z is equals to summation of this thing, this whole part, and that must be equals to 1 to normalize the equation. So at the end, when you when you can see that this normalization constant that must be 1 is equals to this one. The conditional probability of z. What is z? Z is complete set. The complete set of the measurement. Okay, and given x, we already know the x. We already know the random variable x and its periodic PDF. So then we will follow this thing. Given x, we already know the x. Now we will find the next scale x. This is a posteriori, means the time after means ahead. This is behind. We already know this way. Now the next time value we will find this one using this formula. So non-Bayesian approach means we use the likelihood function. Okay, so in the non-Bayesian approach there is no periodic PDF. Okay, we don't know any p of x. We don't know any p of x. We just know that there is any x naught. There is any x naught state, but we don't know its periodic information. What is x naught? X naught is our desired target or something other. We don't know. So there is no periodic PDF associated with the parameter. Thus, one cannot define a posteriori PDF for it. So if you do not know this thing, you cannot find this thing. Okay. So in the non-Bayesian approach, this is unknown, so you cannot find this one. So in this case, one has a PDF of the measurement condition on the parameter. So in this case, we have a PDF of this thing. Okay, but we know the measurement set. We have sensor output. Okay, given the x naught. So here x naught. Okay, so in this case one has the PDF of the measurement condition on the parameter called the likelihood function of LF, likelihood function of the parameter. So this PDF of the measurement condition on the parameter is the likelihood function. Is a measure of how likely a parameter value is given the obtained observation. So what is likely is, you can say, the most likely match, most likely that you are the part of this measurement. Okay, so likely is some kind of probability. Okay, so it's a measure of how likely a parameter value x is given the obtained observation. So we denote the likelihood by this one, lambda, given lambda of x parameter based on the measurement observation is equals to PDF of the z given x. So there are two ways to write either this one or this one. Both are same. You can write this one or this one as easy. Okay, so lambda of x at scan k equals to PDF of z k condition on x. So there are two ways to write the likelihood function of the parameter x. Okay, clear? Then maximum likelihood or and maximum a posteriori estimator. In this section we will study this thing, definition of ML and MAP estimator, MLE versus MAP estimator with Gaussian period, MAP estimator with diffuse period, and likelihood equation. Now what is the maximum likelihood estimator? This is a method for estimating non-random parameters and is the maximum likelihood method that maximizes likelihood function. Equation number 2. This yields the maximum likelihood estimation MLE in equation number 4. So in equation number 2, what is the lambda of x equals to PDF of z given x. Okay, so if we put the maximum of x means parameter, so maximum likelihood of the parameter, this is our argument, and this is a likelihood function lambda of x based on z parameter, z measurement observation. So this estimator is called the maximum likelihood estimator. So that maximizes the likelihood function. If we solve this thing, this will maximizes, this will calculate the maximum likelihood, or this will calculate the maximum peak value of the measurement of the parameter. You can note that while x is an unknown constant and this thing being a function of the set of random observations, z is a random variable. This is a random variable and this is unknown constant. Okay, the MLE is a solution of the likelihood equation like this one. So we will solve this by applying the derivative. So we will apply the derivative over this function and equate this function equals to 0. Okay, for example, parameter estimation. Okay, for example, rolling a coin. Okay, flipping coin. If I have a coin and if I flip it, then what's the probability that it will fall the with head up? Okay, suppose I flip the coin 5 times, and out of 5 times, 3 head comes. 3 head comes and 2 tails. So then the estimated probability is 3 upon 5, and frequency of head. This is we say frequency of head. So this thing is calculated using this formula. Okay, using this formula, and this we apply derivative to this one. How? Okay, let's solve this problem. Okay, if you flip a coin 5 times and you have been asked that what is probability if you flip up a coin 5 times, it will come head. Okay, so why frequency of head? How good is this estimation? So frequency of head is exactly the maximum likelihood estimator of this for this problem. Maximum likelihood means number of head is 3, the maximum value is 3, and the minimum value is 2. The same. This we say that IID, independent identical distribution. These things are identical variable. Means suppose this is United States coin. If there is a South Korean won, then this is not identity coin, identity variable, because there is a Korean won and there is a United States won, United States dollar, then there is no identical. So all coins have same currency, means identity variable. So all variable have same, you can say, identity. All variable have same identity. This is called the identity variable, and these are independent to each other. This coin is not independent, is not dependent on other coin. So these variables are independent, identical, distributed. So of course we can see that 3, the maximum likelihood of this parameter is 3, and z is all, z means how many measurements, 1 2 3 4 5, z is 5, and out of z we estimate the non-random parameter like head 3. So MLE has nice properties. The interpretation and statistical guarantees is simple. Okay, suppose the data is given like this one. These 5 points, x I equals to 1 to n. Okay, n is number of the data. There in our case we have 5 data. Then it's 1 to 5, and xi belongs to head or tail. So theta belongs to head, and 1 minus theta denote the tails. Choose theta that maximizes the probability of observed data. So this is our data. Data includes this thing, this state xi. Now we apply the maximum likelihood estimator formula like this one. So our formula is this one. We apply maximum value of theta, and it's a probability of d given theta, and this not necessary that we use d or theta or z or x, any variable. This just the way of writing equation. So this is the data, the observation, the total observation, and this is the you can say the random parameter that you are finding about using the estimator. So we can see that this data has independent draws like x1, x2 and xn, and this x1 is an event is condition on an event. Okay, this is any event, condition on event, and x1, x2 are any independent draws. Okay. Okay, so we simply put it a product, because this is a sum of product. Okay, now we just separate this thing, because we know this thing is included the head and tails. This function is equals to head and tails. So we just separate this thing. This is head and this is the tail, identically distributed. So for the head is xi equals to head, and for the tail xi equals to t. Okay, because we know the function is equal to this thing. Now suppose we denote this thing as a j theta. So we just remove the product, and theta belongs to head. This is subscript, theta superscript, and this alpha has a subscript of h. That means theta is for head. This is just notation, so don't be confused. This is just notation. This is head and this is the tail, and we just denote that this function equals to j of theta. Now apply the derivative. Okay, now apply the derivative. So Here we apply, we can see that two variables are multiplied. So we apply u into v differential formula. So u in this v derivative this with respect to theta. So u into v u know u into v differential formula. So we differentiate this thing with respect to theta, then this comes. And here after we solve, we can find that the head alpha head equals to total number of the observation, means head plus tail. This is head divided by head plus tail. So that's exactly the frequency of the head. Okay, very simple. We apply, we just do the differentiate with respect to theta. In this case, suppose this is u and this is a v. So what is u into v formula? U into formula, first differentiate, keep the u same, differentiate v, minus v same, differentiate u. You know, do you remember how to differentiate the multiplication of two variables? Okay. Now this is our estimator formula. So how good is this MLE estimation? Head is 3 and 3 plus 2, 5. So 3 over 5. So if the coin, if the I flip the coins 5 times, then 3 heads, 2 tails, then 3 upon 5. If I flip 30 heads and 20 tails, then 30 over 50. Okay. And similarly Gaussian, if we have Gaussian, then we apply same formula, differentiate. So this is independent draws, and because the observation has this value and this is a random variable. Okay, this observation has x1, x2, x3 up to n, and this is our random parameter. Then if our problem is to estimate the Gaussian mean and variance, then we put the formula here in here, because p of x, our independent draws are the Gaussian mean and variance. Then put it here. This is our Gaussian problem, and this is identically distributed. The problem must be independent, identical, distributed, IID. Okay, so independent draws and identically distributed. And now the sum maximum value. Now we have to choose theta, which that maximize the probability of the observed data. Theta equals to nu, means mean and variance. So maximum, we should take the theta maximum value as a mean and variance, and this is a function of this one. And then we assume that this equals to j theta. Then differentiate with respect to theta, and theta is equals to mean and variance. So then this thing will occur. So this is estimated mean, and this is estimated variance that is calculated after applying this formula. Okay, clear?
Okay.
Now map estimator. In this case, we know the priori information p of x is already known. Okay, so we apply just Bayes theorem. And what is map estimator? Here we put maximum value of x at the Bayes formula. This is our Bayes formula. Okay, so corresponding estimate of a for random parameter is the maximum of posterior estimator, which follows from maximization of the posterior PDF. Okay, so this is a posterior PDF or Bayes formula. P of z equals to that you know 1 upon c into P of z condition of x and periodic information P of x. So 1 upon c is just normalization constant and is always equals to 1, so we can just ignore. So then we are applied the maximum of x at this Bayes formula, and similarly the map estimator depends on the observation z, and the realization of x is a random variable. So okay, for example, given the single measurement z equals to x plus omega of the unknown parameter x in the presence of noise measurement w, assumed to be normally Gaussian distributed random variable with the zero mean and variance. Okay, now first assume that x is unknown constant. First assume there is no p of x. First assume there is no p of x. It means there is no p of x means that x is unknown constant and no periodic information about it is available. The likelihood function of x is given by this thing, that we always find the z given x, but we don't know what is x. We do not have periodic information about the x, but just we know the parameter, that this is any random parameter, and this is our measurement z, and having a Gaussian distributor with mean and variance, and this is equals to this thing. Okay, then we apply first maximum likelihood. Why we apply maximum likelihood? Because we don't know p of x. We do not know. First we assume that we don't know p of x. If we know the p of x, then we will apply the Bayes theorem and we will apply the map estimator. But if you do not know p of x, there is no periodic information or there is no periodic distribution of the x, then we will apply the maximum likelihood of the x. So when we maximize this thing, when we find the likelihood of the x, this will equals to z, because there is only single measurement. There is only single measurement x. So what is likelihood of x? Likelihood x is z. So since the peak or mode of 8 occurs at x equals to z, because there is only single measurement and we don't know any prior information p of x, then the peak or mode of 8 occurs at x equals to z. Now next assume that the periodic information about the parameter is that x is Gaussian with mean and variance, that is p of x. Now suppose p of x is given, and p of x is given as a Gaussian variable, means it has a mean and variance. Okay, it is also assumed that x is independent of w, then posterior PDF of x condition of observation of x condition of observation z is by Bayes formula, this thing. So this is same formula equals to 1 upon c is a normalization constant, and e over this thing. This is the same thing. This is the same thing, but if we here we do not know the period information, and now if we know the period information, then we include this thing. And suppose this is 1 upon c is a normalization constant, which is independent of x, which guarantees that PDF integrates to unity. So this is a difference. This is a difference between MLE and MAP estimator. Okay, understand? When we apply MLE, if there is no P of X, then we apply the MLE. We just apply the maximum likelihood, and we just calculate or differentiate our given parameter like P of Z condition of X, and equate it to 0. And if we know the penile information like this one, then we apply the Bayes formula. So after rearranging the exponent in the above equation 10 by completing the squares in X, we have, you can drink water. So in the next step we are solving the squares over the exponent. So by completing the squares in X, we have this thing, now we are this is the this thing, we solve this thing like we are epsilon Z in this one. If we solve this thing or take common variable and addition and subtraction and add here, we take a common variable or LCM and solve the squares. If you open the bracket of this square bracket and try to solve, then this equation will come. Okay, so we are this variable this maximizes of 11. This variable is maximizes of 11 with respect to x, yields x of max equals to eta of z. This is the maximum a posteriori estimator for the random parameter x with a periodicity of 9. With periodicity of 9, this thing is the maximum a posteriori estimator for the random parameter x. So this is actually what happened when you apply the Bayes theorem. You first calculate this thing. Okay, it means when you apply this formula in your program in MATLAB or in any other software, you just write this MATLAB code and just like you have to write this thing at the exponent of e, means exponent of e into this one. So this is equal to this one. Okay, so here we just add up a mean plus this variance and we subtract z minus the mean. Z is our observation and this is the distance. This is the distance between the observation and the mean value, and this is the variance, and mean is added to this one. So we just update. This is already known. We already have calculated the mean value. Okay, we have just added find this value using the maximum likelihood MLE. We have find the MLE and find this value by maximum likelihood function of x given z, and then we just add up this thing, this formula at here. Then we can find the Bayes formula, and we can find the a posteriori PDF using this formula. So equation 13 is the maximum a posteriori estimator for the random parameter x with the periodicity of 9. Okay, so next we We'll discuss in the next class. Okay, is there any question? Clear? So can you tell me what is difference between MLE and MAP estimator?
It's difficult.
Hmm? Hmm?
question.
Huh?
MAP. Why use A?
Yeah.
So name MAP. Why use A?
Here.
No, so just name.
Name. Yeah.
Yes. So
약자가 왜
Because-
maximum 아니 maximum maximum A posterior like there's why A?
This is maximum likelihood, and this we actually compare. We apply the both thing. We use the both things, MLE versus MAP estimator. So actually this shows the difference between the MLE and MAP. When you need to apply only MLE, and when you need to apply the MAP. So you can apply the both together, and you can apply only one thing. So this topic is just the differentiation. This thing tells you, if you know the P of X, then you have to apply MAP estimator. If you do not know the P of X, then you have to apply MLE. So MLE finds the maximum likelihood and gives you output without any prior information, without any P of X. And MAP knows the prior information P of X. Using the P of X, it will find a posteriori PDF using the bias formula. So this apply bias formula because it is given the P of X. So it will apply the bias formula. So like this one.
그 맥시멈
So
조이.
어가
this
그냥
어가 관사예요. 관사입니다. 아 잠깐만. 그
그런 거 같아.
애플 할 때.
그냥
on 애플 할 때 관사. Y A
why A?
not Y not B C Y A I don't understand Y A
Because this
yes.
if you find the using the internet a posteriori, it means we are finding the value a time after. Means we are finding the value next time. I am here, but I do not know this position. So I here estimate what will be the next position. So this is a time of, this means we are calculating some diameter for the next time scale. Estimating given the previous state. It means if you know if you know her location, then you can go to her. It means her location is given to you.
로케이션.
응? 어떤 거?
그러니까 오빠가 저한테 오고 제가 또 오빠한테 가고
음.
그렇게 한다는 거 아니에요? 에스티메이션 할 때?
에스티메이션 할 때?
네.
So if you do not know her location, then you apply the maximum likelihood estimator. You apply maximum likelihood, like you think that she was first I meet her at that location, then I meet her at that location, then I meet her in that location. Then you calculate what is maximum possibility that I can find her here. Okay, you first meet her uh, at some other location, and then you meet her in the classroom. Then you just maximum likelihood calculate the what's the most likelihood that she will be there. So this is maximum likelihood estimator.
Yeah.
But if her location is already known, that she lives here, then you apply the p of x. P of x is her position.
Yeah.
Then you apply the bias formula using her next location. When she will go, when she will left. Okay. So p of x is and this thing is a time after, means the next time value, means k plus 1 value. This is k plus 1 value. And a priori, if we write a priori, then k minus 1 value. K minus 1 is a priori, k plus 1 is a posteriori. And then we just differentiate this. This topic is just tells you the when shall you use MLE and when shall you use MAP estimator. So here, if you have a single measurement and then if you do not know any period information, if you do not know p of x, then apply MLE estimator. This is MLE estimator, and MLE estimator is just maximum value of x. When you differentiate this thing, you will comes at z, because there is only one value. Okay, there is one value z and x, and then if there is a non-period, if you know there is a p of x, then you have to apply Bayes theorem. So in Bayes theorem, we just add here minus z minus x whole square divided by 2 and variance, like this one. And then you apply, you just solve the this equation, then this will come. This is maximum estimator. So this thing equals to this thing, and this thing is the is maximized a posteriori estimator. So now in this case you don't have to differentiate. You already solved this equation. You already solved this equation, and then here now this value is maximized the a posteriori estimator for the random parameter x. Okay. Okay, you can stop the video.